We're now going to take a look at something called a derivative. We'll define what this is, and then we'll introduce some notation for incorporating it into our mathematical work. We'll begin doing this by generalizing the idea of a tangent line slope a little bit. And then we'll say what a derivative is, we'll introduce some notation and some vocabulary to go along with it. So let's begin by taking another sort of more general look at the idea of the slope of a tangent line. Recall that the slope of a tangent line is a line that touches the graph of a function f, or excuse me, a tangent line is a line that touches the graph of a function f at a particular point where x equals a and nowhere else. And we know how to find the slope of one of these things. This is something we also call the slope, we also call the instantaneous rate of change of f at a. And we saw how we can define this using this limit, a limit of the difference quotient of f at a. Now, in the examples we've looked at up to this point, a has been a fixed number like 2 or -1 or something like that. And what that gives us then is a numerical slope, a single number for the slope of the tangent line at that particular point where x equals that number. What we're going to look at now is what happens if we let a continue to be a variable rather than assigning it a specific fixed numerical value. So let's take a look at an example first to see what this looks like. Say we want a kind of formula that will give us the slope of the tangent line of the x squared function at any value of x, so that rather than having to work with this complicated looking limit every single time, we can just plug in the value of x that we want, and this formula will just give us the slope of the tangent line there pretty much in one step. Well, to find this, we'll use our ordinary limit formula for the slope of a tangent line, but where we normally had a constant in a place, we're going to just keep a variable x there. So we're going to look at this limit right here, the limit as h approaches 0 of f of x plus h minus f of x over h. Notice that x here is appearing as a variable. Since the function we're working with is the x squared function, we can fill that in. We have x plus h squared minus x squared in the numerator. We'll expand x plus h squared using the usual formula for squaring a binomial. Notice that we can now cancel the x squared terms that appear in the numerator. We can then cancel a common factor of h that appears in each term of this fraction. We're left with the limit as h approaches 0 of 2x plus h, and we can find this limit by substitution. We're going to let h be 0, but notice we're taking the limit as h approaches 0 here. X is still a variable, so we're only going to substitute 0 for h, not for x. And so that leaves us with 2x. Notice that this is an expression in terms of x. And so now, once we pick the value of x where we want the tangent line to be, or where we want the tangent line to touch the graph of y equals x squared, all we need to do to find the slope of the tangent line is to multiply that value of x by 2. We don't need to do all of the work of simplifying to find this limit every single time. Let's take a look at how this appears graphically. We'll look at the tangent lines of the graph of y equals x squared at the points where x equals 1, 2, and 3. So here's the first one. In blue here, we have the graph of y equals x squared. We've got the point, you can see it plotted there, the point 1, 1. And the red dashed line is the tangent line of x squared at that point where x equals 1. And that line has a slope of 2. 2 times 1, since 1 is the value of x that puts us at that point. If we change our point to, say, the point 2, 4, notice that our tangent line changes along with it. And since we know the value of x that puts us at that point, it's where x equals 2, we saw a moment ago that if we multiply that by 2, we will get the slope of that tangent line. So it's 4. And if we go to where x equals 3, we've got a different tangent line, And to get the slope of that tangent line, we multiply our x coordinate of our point by 2. 2 times 3 is 6. So in every case, the slope of the tangent line is 2 times x, where x is the x coordinate of the point of tangency, the point where the tangent line touches the graph of the function. And we didn't have to use any limits to find those slopes because we already did the work once to do that for any value of x. Now, what we just found here, without calling it this, is the derivative of x squared. So again, notice that when we found this formula for the slope of the tangent line of x squared at a given value of x, we obtained 2x. Now, 2x and x squared are both function expressions, and they have the same independent variable, x. So there's a relationship here between two functions. There's the function we started with, x squared, and there's the function that gives the slopes of the tangent lines of x squared at various values of x. That's the 2x function. So to name this relationship, we will say that 2x is the derivative of x squared. And we can, again, generalize this and talk about the derivative of any function. So if we have a function, f of x, the derivative of it is another function of x. So it has the same independent variable. And the second function, the derivative, gives us the slope of the tangent line of f at x for any permissible value of x. And we can define this in terms of f as this right here. The limit as h approaches 0 of f of x plus h minus f of x over h. That expression there defines a function of x, and it's the function we call the derivative of f. Now we're taking a limit of a difference quotient, as we know, and so the name for the process of finding this is differentiating f. That's what we call the process of finding the derivative of f. Differentiate here comes from the word difference in difference quotient. And the study of all this stuff, the study of derivatives and differentiation and all of that, is differential calculus. So we've alluded to this up to this point, but now we're really starting it in full. The central question for us as we study differential calculus will be, how do we find the derivative of a function? Let's say a little bit more about derivatives by looking at some notation for talking about them and some vocabulary associated with them. To do this, it helps to know a little bit about the history of calculus. So if you go way back to the ancient world, you can find mathematicians doing things that look like calculus. For example, Archimedes, who was the greatest of the mathematicians in ancient Greece, developed some ideas that were basically versions or anticipations of integral calculus. We're going to study integral calculus later after we finish differential calculus, but Archimedes came up with some of the core ideas of it on his own back in ancient Greece. But the full details of all this didn't get worked out until much later. You have to go to the 18th century. And the two key figures here are people you might have heard of, Isaac Newton and Gottfried Leibniz. And one kind of interesting thing that happened is that Newton and Leibniz developed their ideas independently of each other. They weren't talking to each other or exchanging letters or anything like that. They just happened to come up with these ideas at roughly the same time. And in fact, there was a kind of bitter dispute for several years between Newton, Leibniz, and their friends and colleagues about who should get the credit for coming up with calculus first, since they both kind of did it on their own. We don't need to worry about any of that. But the key thing for us here, the reason why this is important, is because Newton and Leibniz did this stuff on their own, and so they developed their own sets of symbols for derivatives. And they aren't the same. Newton had his symbols, Leibniz had his. And both of them are still in use. And Both of them have pros and cons, or advantages and disadvantages. Furthermore, if you're going to take the AP Calculus exam, you'll need to be familiar with both types of notation. So we're going to get acquainted with both of them. We'll start with Newton's notation. What we're actually looking at here is a variation of Newton's notation that's a little bit easier. It was developed by a mathematician named Lagrange, but it goes back to some of the things Newton was doing. So we'll call it Newton's notation. Newton's notation for derivatives involves using a symbol that we call prime. A prime symbol looks a little bit like an apostrophe, but it's not rounded. It's that very, very small little mark you see there. And we use the prime symbol to indicate when one function is a derivative of another one. So in other words, if we have a function f of x, and we want to talk about its derivative, we denote that with what you see there. We have f followed by the prime symbol, and then the x there marking the independent variable. And we read that as f prime of x. You can also sometimes just write f prime without anything to indicate the independent variable if for whatever reason you don't need to mark the independent variable of the function. And so, for example, we saw earlier that the derivative of x squared is 2x. And so if f of x is x squared, then it would be correct to write that f prime of x is 2x. And you can modify this a bit depending on exactly how you're describing your function. In particular, you can use prime notation as well with dependent variables rather than function symbols. So in other words, if you've got that y is equal to f of x, so y is the dependent variable of the function f, then you can also write y prime to denote the derivative of f. So again, if y is equal to x squared, we can write that y prime is equal to 2x. So that's Newton's notation. It's relatively simple. Leibniz's is a little more complicated. It's also the case, though, that because Leibniz's is a little more complicated, it's more informative. There's more stuff there to tell you what's going on. To see where Leibniz got his notation, which we'll introduce in just a second, go back to the symbol that we sometimes use for the slope of a line, delta y over delta x. Recall that delta y and delta x here denote changes in the values of y and x. And when we're calculating the slope of a tangent line, which is what a derivative gives us, what we're interested in is what delta y and delta x are when those changes are very, very, very small. So what Leibniz did was to modify this slightly. Rather than using the Greek letter delta, he used the lowercase Roman letter d to denote very, very small changes in the values of y and x. So he'll write dy and dx for a small change in y and a small change in x, respectively. And then we can denote the derivative of the function that we're looking at as what you see there, dy over dx, where y is the dependent variable of our function and x is the independent variable. If you want to read that, you can read it either as the derivative of y with respect to x. That's one way to read it. Or to save time, we'll sometimes just read the letters one by one, dy dx. That's Leibniz's notation for derivatives. Now, I said that we read that as the derivative of y with respect to x. What does that respect to x part mean? So the derivative of y with respect to x is kind of a long, unwieldy phrase. Why is it all there? It might seem sort of pointless. Why not just say the derivative of y? Well, the with respect to x part, of course, indicates the independent variable of our function. So if you hear the derivative of y with respect to x, you know that the independent variable of the function y is x. We could just say the derivative of y and leave sort of implicit the independent variable. But if you go on to study more advanced calculus, one thing you'll start to do is to look at what happens when functions have more than one independent variable. And in those cases, it's really critical to keep track of which independent variable value you are changing in order to produce a change in the dependent variable. Leibniz's notation allows us to do this, and saying the derivative of y with respect to x, or the derivative of y with respect to t, or something like that, makes it easy to keep track of which independent variable is being changed. And that often affects the change in the value of the dependent variable. Now, in this course, we're not doing anything with functions that have more than one independent variable, but it's still good to get used to the notation, the vocabulary, so that when you do study that more advanced calculus, you're ready for it. This is one advantage, by the way, of Leibniz's notation. Newton's notation is not as well suited for functions that have more than one independent variable. And so when you do more advanced calculus, often you use Leibniz's notation almost exclusively. There are some slight variations on Leibniz's notation to deal with the different ways in which a function can be presented to us. So here are some modifications you'll see of Leibniz's notation. Just to take an example, let's say that we've got a function f, independent variable is x, the dependent variable is y. So y is equal to f of x. And let's just say that f of x is always equal to x squared. Here are some different ways to denote that the derivative of the function in question here is 2x. We can write that dy dx equals 2x. That's what we just looked at. We could also replace y in the numerator with the function name f and write df dx. Means the same thing, still equal to 2x. You can also put the algebraic function expression into the symbol and write something like what you see there, which we often read as d dx of x squared. The reason why we put x squared in brackets after the d dx thing instead of up in the numerator is just to avoid having things get too cluttered. If we had dx squared in the numerator, there would be a lot of stuff with an exponent. It would be quite hard to read. This makes it a little easier to read. By the way, when you do that, when you have the function expression after that d dx symbol, it's customary to enclose it in usually square brackets. You'll see other grouping symbols sometimes as well, but make sure you're putting some kind of grouping symbols around that to indicate which function is being discussed or which function's derivative is being presented. There's a little bit more to Leibniz's notation. Let's look at something called differentials. Notice that this symbol dy dx is formatted like a fraction. We've got dy in the numerator and dx in the denominator. And that's a variation of the delta y over delta x symbol for the slope of a line. Now, delta x rather, and dx, whether we use delta or d, we're talking about changes in the value of x. And if you have y instead of x there, you're talking about changes in the value of y. Recall that the d instead of delta just denotes that we're talking about a very small change to the value of the variable. And we call that symbol by itself, dx, a differential of x. Now, as we study differential calculus, we will usually see these individual differentials like dx or dy in the context of larger derivative expressions. So things like dy dx or dh dt or whatever your variables in question are. You might also see stuff like ddr of pi r squared, maybe if you're doing something with the area of a circle. So notice that here the differentials in question, like dy, dx, dh, and so on, all appear inside these expressions that we use for derivatives. Near the end of our study of differential calculus, we will look at one situation where we might want to separate these differentials from each other, and that will become much more important in integral calculus. So you don't need to worry too much about this right now, but just keep in mind that these symbols do have names. They're called differentials, and in at least some contexts that we'll look at later, they appear separated from each other. Finally, there's some vocabulary associated with derivatives. So when we have a function and we find its derivative, we have another function. This other function, the derivative function, gives us the slopes of the tangent lines of the original function at various points, whichever point we choose. You'll also see the word derivative used in phrases that denote the slope of a particular tangent line. So we might say that we're finding the derivative of a function at a, at 2 or at -3 or something like that, where that's just going to be a number. A here will be the value of x where the tangent line touches the graph, what we've been calling the point of tangency. And so what this means in practice is that there are 3 phrases that you'll see again and again and again in calculus that all mean the same thing. We can talk about the slope of the tangent line of a function at a, or the slope of the function at a is a kind of shorthand for that. We can talk about the instantaneous rate of change of a function at a, and we can talk about the derivative of the function at a. These are all 3 different names for exactly the same thing. And they correspond to different ways of studying functions. The first one is a kind of graphical interpretation in terms of a slope of a line. The second one is we might call a dynamical interpretation in terms of how something is changing. And the third one is a kind of analytical one that involves thinking about the derivative function and then its value at a. When we're talking about a derivative at a particular point, we need to modify our notation for derivatives slightly. We can do this in both Newton's and Leibniz's notation. Let's say that y is equal to f of x, and we want to talk about the derivative of f at a. In Newton's notation, we just write f prime of a. F prime of x is the derivative function, and f prime of a is its value at x equals a. So that's easy enough. That's just using our usual function notation. Leibniz's notation is a little trickier here because there's not a convenient place to put the independent variable or a value of it into the symbol. So we force it a bit. We'll write dy dx, that's our symbol for the derivative, and then we'll put, after a little vertical line segment, x equals a as a subscript. So that tells us that we're calculating the value of the derivative function at the point where x equals a.